Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. This is the conclusion of the lecture entitled Solving Systems of First Order Differential Equations. And the last case we need to think about is when we have a multiplicity of the eigenvalue greater than 1, and since we're doing 2 by 2 matrices, that means it's going to have a multiplicity of 2. So this is the differential equation, the system of differential equations that we're solving. This is the matrix of the derivatives of x1 through x2 is equal to, this is the 2 by 2 matrix, and that is x1, x2 again. Now, we're good to go with this because we know very well how to find the eigenvalue and the eigenvector. But we need a second linearly independent solution, and we don't have one here. We only have the one. So we need to find another one, and we might make a good scientific wild-ass guess saying, oh, it worked before just throwing in a factor of t, so maybe that'll work this time. That's not a bad way to do science. That's not a bad way to do business. I've read business books that say do ready, fire, and then aim. And I know from my experience doing math, guessing, checking, and guessing again, perhaps better, is not a bad way to do math. So let's check and see what happens. So we're going to be substituting the t times the eigenvector and e to the lambda t into this equation and see what happens. So here we just substitute in, and that's a times that vector. But then what happens is on this side, what we're going to be doing is we're saying x is equal to that. So this is going to be the product rule. So it's going to be the derivative of the first, which is going to be 1 times this, plus the first times the derivative of the second, which is going to be lambda eta, the vector, t e to the lambda t is equal to that. Now we can move everything to the right hand side and set it equal to the 0 vector. But what that means is that a minus lambda I of the eigenvector equals 0. We knew that. But also, since the exponential can't be 0, that means that this has to be 0, but that can't be an eigenvector. So this is not a correct guess. So we need to fix this, and the thing we need to fix is this thing is getting in the way. The eta e to the lambda issue. So we need to fix that. So let's have a new guess, and this time we're going to guess again, and we're going to say, well, let's try vector x is equal to what we started with before, but now we have a correction factor that we're calling e to the lambda times, and this is the Greek letter called rho. I know it looks like a p, but it is a rho, and that is a vector, and this is an unknown vector that will determine as we plug in and see if this will work. So we're guessing and checking again. So we plug it in and we take the derivative. Now this derivative, and you should verify this, but this is the derivative of that new thing that we plugged in. You see the rho being there, and so we are using the rules for calculating the derivative, but we're adjusted by this factor. But if we move everything to the right hand side, then we know we have the 0 vector over here, so I can set all the coefficients equal to 0, and so we get this is equal to 0, but we knew that since that was an eigenvalue. But then we know that to make this one equal to 0, this has to be true, and that means that the vector rho is a solution of this set of equations. So therefore, the second solution is going to be this. You really need to verify that this is linearly independent, but it will be as long as you pick rho to be the solution to this. And again, you need to check the linear independence. I'm not doing that here. Okay, an example's worth 1,000 words, so why don't you give this a go? You know what to do. Let's see how you do. Okay, a lot of this stuff should be very old hat by now. We're going to find the eigenvalues, so we take the determinant of a minus lambda I we do this, and we get, after we simplify this, lambda minus 5 whole squared. That means that the dual, or the double root here, the double eigenvalue is 5. So we got a double eigenvalue, and we'll find the n eigenvector associated with that. So we'll solve this. We're putting 5 into this matrix and solving this equation, and we find that this is true again. Those rows are identical. They're multiples of each other. So I can just use the top row, and that simplifies to this, and I can then substitute in and find my eigen vector to be 1 minus 2. But now I need to find what row is. So what I'm going to do is I'm going to take a minus lambda row is equal to this value. So I need to solve this. Now again, this is still a dependent system, and so I'm going to get this and this, which I will write this way. And now I get to pick something, and here actually I can, without any danger, because this isn't really an eigen vector, I can pick row 1 to be 0. If I do that, I get that one value that will work for row is 0, 1. Okay, so now I can write down my solution. So x of t is equal to, this is c1 times e to the 5t, this, plus c2, and here is this with my corrected row. And then we can apply the initial conditions, which are way up here. And we get two equations in, two unknowns, and we can figure out what C1 and C2 are. And so the solutions is going to be, and we're doing some simplification as we go along here, but this is going to be the solution at the end of the problem. Here's another example. You know what to do. Let's see how you did. Okay, again, like it's old hat, we're going to set up the determinant of a minus lambda I, and we will get that the root of multiplicity 2, the eigen value, is negative 3 over 2. And that means we can substitute negative 3 over 2 into here and do the calculation, and to find the eigen vector. We'll find that the eigenvector is minus 3, 1. Again, you should verify that you're doing all of these calculations. Now what we're going to do is we take this a minus lambda I, and this is our row vector, and we set that equal to our eigenvector, and we solve this. And this time we're taking row 2 to be 0 because that's the way I simplified it. So what we get is this is going to be minus 6 comma 0. So the general solution for the system is this. And when we apply the initial conditions, which are up here, we're going to get two equations in, two unknowns. Now notice that some of these coefficients have e's in them. That's still okay. So C1 is e cubed over 3, and C2 is minus e cubed over 6. So I put those in, and I will get this as a solution. When I simplify that, and I can do that by combining these exponents, I move the third in there, and so this is mostly just arithmetic with vectors. So I get the final solution is e to the minus 3 over 2t plus 3, that's in the exponent, and this vector is 0, 1/3, plus, and this is going to be t, this is e to the minus 3 over 2t plus 3 again, and this vector is 1/2 and minus 1/6. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.